This video covers section 11.5, infinite geometric series. We have three objectives. We will start by determining whether an infinite series converges or diverges. Then we will find a formula for the sum of an infinite geometric series, and then we'll finish by writing repeating decimals as fractions. Okay, so to start off with, what do we even mean by an infinite geometric series? So we've been adding geometric series in the previous section, but they've all been a finite sum of terms. You start off with a geometric sequence, and then you add up the first 5 terms, or the first 10 terms, or the first 20 terms. What we want to look at now is take that same geometric sequence and add up every single number in the sequence, the entire thing, an infinite geometric sequence. Now, intuition would say that that's not going to have a sum. That's just going to blow up to an infinite number. However, there are certain conditions where it will actually have a sum. So let's look at an example of what we mean by a convergent infinite geometric series. So consider this geometric sequence that starts with 2, and then we're multiplying each number after that by 1/2. So this is a1 is equal to 2, and r is equal to 1/2. So you can see that the subsequent terms are actually decreasing. Now we're going to look at the sequence of partial sums. The partial sums are the sums of the sequence where they terminate, meaning that just like we did before, S1 is just the first term, S2 would be the sum of the first 2 terms, S3 is the sum of the first 3 terms, etc. And what we're looking at is the values of these. What happens to these as n increases? And what we're trying to do is we're trying to find S sub n and make n go as large as possible. The way we write this is really something that we do in calculus. We say we're looking for the limit of S sub n as n approaches infinity. What do the values of these tend to do when we make n larger and larger? So as we look at these, you start to see a pattern. They are increasing, but they're increasing less and less. And I've actually plotted them out, at least the first 9 terms here on this graph. And you can see that, this is the first one was 2, then 3, then 3.5, and they're all getting closer and closer to this value of 4. You can see they're getting, just by the 6th term, it's really quite close to 4. Well, it turns out that you can keep going, and it just continues to get closer and closer to 4, but it never actually quite gets there. We can make the value of this sum as close to 4 as we like just by choosing an n that's sufficiently large. So for example, S1000, we could compute this. We could actually do it right now because we know the formula for Sn is a1 times 1 minus r to the n over 1 minus r. So we could just plug everything into this. So a1 was 2 times 1 minus 1/2 to the 1000 over 1 minus 1/2. You could evaluate this, and chances are, I'm not sure your calculator can even do it. It'll probably give you overflow error, but if you do type that in your calculator, it will probably round it right up to 4 because it'll be so close your calculator won't be able to see the difference. And that's really what we mean by saying it converges. You can make this get as close to 4 as you like by picking a bigger and bigger value of n. So as close as this is to 4, if I go to the 1000th and first term, it'll be even closer to 4, and it just gets closer and closer, but it actually never crosses that line. So this is what we mean by the idea of convergence. So the infinite geometric series, which we're going to typically denote as S sub infinity, or if I just use an S without any subscript, that I mean the infinite sum. We're saying if you take 2 plus 1 plus 1/2 plus 1/4, and you keep going and you don't stop, you literally add all of them, we are saying that comes out to 4, or more accurately, we're saying it converges to 4. If you add up those that infinite sequence, it will converge to 4. Okay, now that doesn't happen with every geometric sequence or every geometric series. Here's a different one. Starts at 2, then goes to 3, goes to 4.5, and up. So we can see, again, a1 is 2, but the r for this one would be 3 over 2, this divided by this, or in other words, 1.5. The R value is 1.5 on this one. Okay, so I did the same thing here, did the sequence of partial sums, and we're looking at what's the pattern, what's happening to these. Well, they're getting bigger, just like they did in the previous one, but not only are they getting bigger, the distance between them is even growing. The distance here was 3, the distance here is 4.5, and you can see it's just getting bigger and bigger at each stage. And you can see that in the graph as well. The sequence of partial sums is growing, and it's growing faster and faster at each stage, and it will just grow without bound. So this series does not converge. There is no number that represents the sum of all of these numbers. So the way we could write this, we could say the limit as n goes to infinity of this series is infinite. So this is one type of divergence. There are actually other types of divergence where a series just oscillates. Instead of just going up in one direction, maybe it goes up and then it goes down and up and down and up and down. This would be another type of divergence. We're not going to see that within this section, but there are other ways things can diverge. For us, they're either going to be infinite or they're going to converge. Okay, one big giveaway, which I kind of already mentioned, one way to somewhat tell, you can't prove it from this, but it's a way to check at the beginning. The only way they're going to be able to converge is if the numbers through the sequence, they're getting smaller, meaning the next term is smaller than the previous, which you can see from this one. It goes 2, down to 1, down to a half, and they're getting smaller as you go. Whereas in this one, they're getting larger each time. Each subsequent term is larger, and that's why it's clearly going to diverge. There's a little more to it than that, but that's definitely a helpful way to think about it. Okay, so let's try to approximate what this series, whether it converges, what it would actually go to if we added up this infinite series. So to do that, the idea is we know that the S sub n is going to give us an approximation for the entire sum, meaning if I pick a finite amount of this, it's going to approximate the actual infinite sum if n is really large. Now, that's very fuzzy. What do I mean by really large? It changes actually depending on which sequence you're dealing with. Sometimes really large could be 4 or 5 terms in. Sometimes you might need to go 1,000 terms in. But the point is, as n goes to infinity, this is the way we could write it. So as n approaches infinity, as you make n bigger, then S sub n will approach S infinity. If it's going to converge, then as n goes to infinity, this should converge to this. Okay, so let's get rid of this. We don't actually need all this right now. What we're going to do, though, is write out S sub n. So we've got the first term we know is 1. R is found by dividing these two, or you can probably just see here what it is, but you can find it by taking 1/3, dividing it by the previous, well, that's just 1/3. So S sub n would be equal to, let's write the formula just in case we forgot. So that's our general formula for the sum of the first n terms. So plug in 1 for A1. You have 1 minus 1/3 raised to the nth power over 1 minus 1/3. And let's clean this up just a little bit maybe. We don't need the 1 there. We can go ahead and subtract the 1 minus 1/3. So this is really 1 minus 1/3 to the nth power over 2/3. If you wanted, you could do keep change flip here to clean it up even more, but let's stick with this. So ideally what we'd like to do is we'd like to be able to just come in here and put infinity here. But what does that even look like? What does it look like when you take a number and raise it to infinity? That's not really well defined. We will see later on that is almost essentially what we're going to do, but right now we can't do that. So what we're going to do is just plug in values for n and see what happens to the value of this, see what it approaches. And the best way for us to do that will be on the graphing calculator. So we're going to put that expression right there in y1. Okay, so put in your fraction. We've got 1 minus 1 divided by 3 raised to, and we're not going to use n, we'll use x as our exponent, and then 2/3 or just 2 divided by 3 in the denominator. Okay, so now let's go to our table, and there's a chance that it's going to give us fractions as answers. If that's the case, we're going to come back and modify this, and it is. So this is going to be a little harder to see what's actually happening if we leave this with fractions. So let's go back to y equals, and there's a couple ways you could fix it. One way is you could just put a decimal point in here. So if I just insert decimal point right there after the 1 and then go to this, you'll see it does round the values now. A different way, because that is easy to mess up actually, is, oh no, okay, we got rid of it. Okay, an easier way to do this is to tell it to convert it to a decimal. So if you just go to math, the very second option, first one is convert to fraction, second one is convert to decimal. So it'll just evaluate that, convert it to a decimal for us, which for this is going to give us an easier way of seeing what's happening. So these are the n values, and over here, maybe let's just maximize this. Okay, so these are the n values, and these are the s sub n values, and we're looking for a pattern. What are they doing? As n increases, are they approaching anything? And you can see it doesn't take long. It looks like it's getting close to 1.5. You can see if I move over here, though, it's not exactly 1.5. It's just getting closer to it. And eventually, the calculator won't be able to round it anymore, and it lost track of the decimal places, so it actually just rounds it straight to 1.5. Even though it's not exactly 1.5 at the 23rd step, it's so close the calculator can't even see the difference. So this is what we would say the limit is. We would say that the infinite sum, if I added the whole thing up, 1 plus 1/3 plus 1/9 plus 1 over 27 plus on and on and on to infinity, that comes out to 1.5, or in other words, 3/2. So that is S infinity. That's the infinite sum of that, or the sum of that infinite geometric series. Now, we don't want to have to do that every time. We would like to have a mathematical way of getting to this number. So before we can get there, we need to do a little bit of investigating. So what we need to do is we need to investigate r to the n in some different cases and see what happens when we take a number and raise it to a power. We're going to break it down into 3 cases. So the first case is we're going to say what happens to r to the n when you pick a number that's bigger than 1. Now we're going to do this in a very, I guess, not a very rigorous way. We're just going to pick a number and look at what happens and infer that it happens with all big numbers, or numbers bigger than 1. So it doesn't matter what you pick. I'm just going to pick r is equal to 3. That's bigger than 1. And what we're going to look at is what happens to 3 to the n. What does it approach as n goes to infinity? What happens to the value of this? And to do that, to investigate that, let's go ahead and look at that on the calculator. You should hopefully already have a pretty good idea of what's going to happen. But 3 to the x, because I don't have an n there. And let's look at the table again. I'm going to go back to start it at 1. Okay, so over here, we're looking at the value of these numbers. And what do they appear to be doing? Well, they appear to be getting bigger. And they keep just getting bigger and bigger and bigger. Notice it's scientific notation here, but down here you can see the full value there. Well, they continue to grow. And it doesn't stop growing, it just gets bigger and bigger and bigger. So what I would say is this grows to infinity. And hopefully that's a very obvious thing. R to the n is going to go to infinity if the r value, if the base of that is bigger than 1. So let's fill that in over here. R to the n goes to infinity as n goes to infinity. We'll see that when this happens in a geometric series, then meaning that if you have an r that is bigger than 1, it's not going to converge because of this term here. Okay, second case. Let's look at when r is less than -1. Well, we might as well just look at -3 then. You can use any negative number. And when we put this one in the calculator, we need to be careful and make sure we use parentheses. So we're looking at that. -3 in parentheses raised to the n power. So let's go back, y equals, and put that in parentheses, and make sure you use a negative sign here, not a minus sign. You'll get an error if you don't do that. Now I want this to start back at 1. So one way you could do that, if you go second window, which is, it says table set up there, you can tell it right now it's going to start at 17. I want it to start at 1. And then this second thing, this delta table that you see here is telling you how much to increment by. We're going to leave that at 1. Okay, so let's make the table again. and look at the values. Well, these numbers really should seem familiar because they're the same numbers as before, but there is a difference here. The difference is it's oscillating. It's alternating between positive, negative, positive, negative. So the numbers are getting bigger, but they're also switching signs. So we can't say that the limit goes to infinity because it's going to a negative, getting larger in negatives, but it's also getting larger as a positive as well. It's alternating back and forth. So what we would just say here is it doesn't approach anything. In calculus, we usually just say does not exist, DNE. Right? There is no limit to this. So this is also going to be bad for a geometric series. If the R value is less than -1, like this, you're not going to get an infinite sum to that geometric series. So we had bad, the first case was bad, the second case was bad. Now, one way to actually write both cases in one is to say absolute value of R is greater than 1, because this is R is greater than 1 or R is less than -1. It actually has both things within this single statement. Remember that absolute value is distance from 0. So this says if the distance R is from 0 is greater than 1, well, that could be this case, or it could be this case, right? Think of a number line. Here's 0, here's 1, here's -1. This is when R is greater than 1, and this is when R is less than -1. So they both characterize when the distance from 0 is greater than 1, whether you're on this side or this side. So in either one of these cases, the series is not going to converge. And we're going to see why because of this term here. Okay, so third case. Third case, we are going to characterize it with that absolute value again. So this is saying the distance R is from 0 is less than 1. So if I make a number line again, same thing. If the distance is less than 1, then R would have to be somewhere in here. It's some kind of number between -1 and +1. So those would be like your typical decimals, your decimals without any unit value, your fractions that are less than 1. So those kind of numbers. So we need to pick an R value like that. So let's do R equals, how about just 1/3? 1/3 is definitely in here. Okay, let's look at what happens to that. Let's look at what happens to if we do R to the n, meaning 1/3 raised to the nth power. Okay, so we make a table of this. Oh, I wanted to start that over at 0 or at 1. Okay, so now we're looking at these values. You can see they're decimal values. And what do you notice if you're paying attention down here? You got to be careful. It converts it to scientific notation. Remember that what this number currently is saying would be like 4.6 times 10 to the -4. This is telling you how many times to move the decimal place back in that direction. Let me actually try to write that out a little bit clearer. So just to make sure we're clear on this. It's not going to let me write. All right, hold on. Okay, I won't be able to do that. Well, maybe now. Nope. All right, sorry. Let's just keep going. So the idea is the more negative this part right here becomes in scientific notation, the smaller the number is. So if I keep going, the numbers are actually getting smaller because this is becoming more and more negative. And I think eventually, I don't know if I'll be able to get there. It's getting worse and worse. But I'm hoping eventually it just tells you 0. Let's see if we go out to 200. Okay, there we go. Picked a good number. So you can see once you hit 208, it can't round anymore. right? It's unable to approximate it any better, so it just says 0. So the takeaway from that is that this will approach 0 as n goes to infinity. R to the n goes to 0. Anytime r is between -1 and +1, it's going to go to 0. And I could go back and do the same thing with -1/3, and you're going to get the exact same result. It does still alternate, but it alternates in a smaller and smaller window, and it converges down to 0. So it goes positive, negative, but it still converges to 0. All right, so this is the big thing. This is the important thing. Anytime you have r to the n, and r is between -1 and +1, that will approach 0 as n approaches infinity. Okay, so that will be enough for us to be able to derive a formula for the sum of an infinite geometric series. Okay, so over here, I've written down the expansion for the infinite geometric series in general, and then I wrote the partial sum. So this would just be the sum of the first n terms. We already have a formula for that. We proved this formula in a previous set of notes. And as I mentioned, the infinite geometric sum series should be approximated by this expression as long as n is sufficiently large. If we pick a large value of n, then this will approximate the infinite sum. So let's unpack this a little bit more. So I'm going to rearrange it a little bit. So notice I'm highlighting here the r to the n because we just talked about how that behaves. So first thing I did is I went ahead and moved a1 to the numerator here. And then I can actually pull this denominator to be just over the a1. Just pull this off to the side. You could think of this as being over 1 if you wanted. All right, so that's just to emphasize this first fraction and leave this kind of hanging out here. Now the reason I did that is now we can analyze what is going to happen to this as we make n larger and larger. Notice that S sub n, the value of this, is completely determined by this part here because these numbers are all fixed. They're not changing. The only thing that changes as you increase n is this part right here. And we said if the r is between 1 and -1, right, that's what this is saying. If r is less than 1 but bigger than -1, then we know that this r to the n is going to go to 0. That piece is going to go to 0. So the way we would typically write this in calculus, we would say we know that if this thing converges, then the infinite sum, the sum of the infinite geometric series, is the limit of this partial sum, which means it's the limit on this expression. And we just said as you make n really big, this thing is going to go to 0. So I can just go ahead and put 0 in there instead because we're making n go to infinity, which means this whole thing is just 1, which means the entire sum is really just that value there. So to show you that this actually works, let's go back to the example we just approximated. Okay, so we just said the infinite sum should be equal to a1 over 1 minus r. And for this problem, a1 is 1, r was 1/3, 1 minus 1/3, so that's 1 over 2/3. And if you do keep change flip, 1 divided by 2/3 is the same as 1 times 3/2. You get just 3/2, which is exactly what we saw with the calculator as well. You can even see what we did with the r to the n right here. We said that we know this goes to 0 as n goes to infinity, so you can essentially just ignore it, and you have 1 over 2/3, which is 3/2. So the formula for infinite geometric series is actually the easiest out of all the formulas that we've had. All right, so that's just, that whole theorem is restated here. If you have an infinite geometric series, you can write that using summation notation by just putting infinity up here in the upper limit. Then its sum is a1 over 1 minus r. But the critical thing, it only has a sum if this is true. If r is less than 1 or bigger than -1. If the r is bigger than 1 or less than -1, right? If it's more than 1 unit away from 0, then there is no sum at all. It does not converge. It's a divergent sequence or series. Okay, so let's try doing that for these two examples here. So it just says determine whether they converge. It doesn't say determine what they converge to, just find out if they converge. And this all comes from the r value. So we just need to find r for each one. So the r for this would be 1 over 2/3. Just take this term divided by its previous term, or you could do that at any point in the sequence. Using keep, change, flip, we see that's 3/2. Well, 3/2 is 1.5. That means r, or you could say the absolute value of r, is bigger than 1. So therefore, this thing diverges. This doesn't have a sum. It would be infinity if it had one. Okay, so we cannot use the formula on it. You will get, like if you plug the a1 and the r into this, you get a number. It's just not what this adds up to. Okay, next one. So r for this one is 16 over 32, which is 1/2. Well, that r is less than 1, which means it will converge. It will have a finite sum, and you can find it using this formula. But it only asked us to determine whether it converges or diverges. Okay, so now let's actually find the sums, again, if they exist. So I always start by finding r because you're going to need it in order to calculate the sum, and you need it to know whether it converges or diverges. So r for this one will be 3 over 8 divided by 1/2. Again, if we do keep, change, flip, this is 3/8 times 2 over 1, which is 6 over 8, but then you can reduce that down to down to 3/4. And 3/4 is less than 1, so we're good. That converges, and that means the infinite sum, we know the formula is a1 over 1 minus r, and a1 is 1/2, so 1/2 divided by 1 minus the r, which was 3/4. Well, that's 1/2 over 1/4. We know that 1 is really 4 over 4, so 4 over 4 minus 3 over 4 is 1/4. And then again, keep, change, flip, you're going to have 1/2 times 4 over 1, which is 4 over 2, which is just 2. So these fractions, this infinite sequence of fractions, it adds up to 2, which is kind of an amazing fact. Okay, next one. So start by finding r. R would be equal to -2 over 1, which is just -2. And that's a problem. That means that the absolute value of this r is bigger than 1. Right? The absolute value of -2 is bigger than 1, which implies it diverges, which means the sum does not exist. This one's not, like, you couldn't even say it's infinite, positive infinity or negative infinity, because it's an alternating sequence. So it gets really big, and it also like really positive and really negative as well. So you just stop here. You can't do anything more with it than that. Okay, next one. R for this would be 4/5. That is less than 1, so we're good. And so we can go straight to the infinite sum, which again is a1 over 1 minus r. So that is 5 over 1 minus 4/5. All right, so again, this is really 5 over 5, which means that denominator is 1/5. Right, we've got 5 over 5 minus 4 over 5 is 1/5. Keep, change, flip, you're going to have 25. 5 divided by 1/5 is 25. Okay, next one. R would be -5 over 25, which is -1/5. Now, a lot of times people get caught off here and they say, oh, it's negative, so it doesn't exist. No, as long as this is between -1 and +1, then it exists. And this is, right? The absolute value of r in this case is still less than 1. So that means it will converge, right? This is a good r for convergence. So we can do the formula. The infinite sum is a1 over 1 minus r. A1 in this case is 25. And we have 1 minus, be careful with your signs here on this one. This one's going to turn into addition. So we've got 25 over, I'm going to write it as 5 over 5 plus 1 over 5, which means this one is really 25 over 6/5. If you do keep, change, flip, that's going to be 125 over 6. So that entire thing does add up to a fixed number. Even though it alternates, that it still adds up to that finite positive number. Okay, let's try doing the same thing, but with infinite geometric series that are written in summation notation. So remember, a geometric series can be expressed as the sum of a1 times r to the n minus 1. These are already in that form. They're using a different index, or I guess that is using n. So this would be n equal 1 up to infinity. This is always a geometric series, but they're infinite because of that. So we can just look at this and tell what a1 is. a1 is equal to 24, and r is equal to 4/3. So then we go straight to the formula. Or do we? Always stop. Just because this is a fraction does not mean that it's automatically going to converge. Notice that this is really 1 and 1/3. In other words, it's 1.3 repeating. This r value is too big. So therefore, series does not converge. So you can't do anything else with that. That's it for that one, right? It doesn't have a sum. It would be infinite if it had one, but it doesn't have one. Okay, so that would have been easy because we could immediately see a1 and r, but it didn't converge. The next one, though, it doesn't look like this, or at least it doesn't look exactly like this. So you can't just immediately go to saying what a1 and r are on this one. You need to do a little bit of work. So a1 can always be found by just plugging in the lower bound. So if we plug the k equal 1 in, we get 2 over 3 to the 1 minus 1. In other words, it is 2 over 3 to the 0. And we know 3 to the 0 is just 1. So a1 is actually 2 on this. To get r, you could go ahead and find a2 and then take the ratio of these. So a2 would be 2 over 3 to the 2 take away 1, which is going to be 2 over 3 to the first, so it's just 2/3. If we take the ratio, r is a2 over a1. Make sure you divide them in the right order. Second term divided by first term. That's going to be 2/3 divided by 2, which comes out to 1/3. Now, if you're clever, you can rewrite this so that it looks just like this. You could, and that would make it so you could avoid all of this. You could pull the 2 over so that this is 2 times 1 over 3 to the k minus 1, like that. And then the other thing you could do is this power, since the numerator is a 1, you can only do this because the numerator is a 1, you could pull the power out of the whole thing there. So it's 2 times 1/3 to the k minus 1. So this represents the same as this, and now you can easily see a1 is 2 and r is 1/3. But this will also work. Okay, so is the r small enough? Yes, it is less than 1, so this converges, which means that the infinite sum, the value of this, is going to be given by a1 over 1 minus r, which is 2 over 1 minus 1/3, or 2 over 2/3. Keep, change, flip. The 2's are going to cancel. Looks like that one just comes out to a solid 3. So that entire infinite geometric series adds up to just 3. Okay, let's try. We got 2 more of these. Okay, so again, this one, it's not immediately obvious what the values are. I think it's a little bit more clear than the previous one. But if you're unsure, then we can do the exact same thing we did before. So a1 is going to be found just by plugging 1 in. So 1/2 to the 1 minus 1, or 1/2 to the 0. And as we said before, anything to the 0 except 0, anything non-zero to the 0 power is 1. So a1 is 1. And then R, hopefully you have a good guess for this because it is kind of staring at you. But if you didn't know, let's do the A2 again. So A2 would be 1/2 to the 2 minus 1, just plugging 2 in for K, which is 1/2 to the first. Obviously, that's just 1/2. So then R would be found by taking the ratio A2 over A1, which would be 1/2 over 1, which in this case is just going to come out to 1/2. This one is pretty much already in the right form. There's an implied 1 in front of that. You could think of this as 1 times 1/2 to the K minus 1, where K equals 1 up to infinity. So here is A1, here is your R. Okay, the R is small enough, it's less than 1, so we can go straight to the sum. S infinity is A1 over 1 minus R, as it has been for all of them. So we have 1 over 1 minus 1/2, which is 1 over 1/2, because 1 minus 1/2 is 1/2. And keep change flip just gives us the value of 2 then. Okay, last one. It looks almost exactly like the previous one, but there is one big difference, and it is right there. So that does impact it. What ends up happening is the R value is still going to be 2/5. That's not the problem. The problem is the A1 value. If we plug 1 in, the bottom index is 1, plug it in, you get 2/5 to the first power, which is just 2/5. So the A1 is not 1 like the previous one because of that exponent. Now, the way we could fix this, make it in the proper form, is I could pull off one of those factors of 2/5. But if I pull one off, that means I have to decrease the power by 1. So I'd have to write that as K minus 1. And now it does have the right form. So now you see A1 is 2/5, and you see that R is also 2/5. You could also find R using the same procedure that we did over here. Okay, so 2/5, that's less than 1, so we're good. So the series does converge. It converges to A1 over 1 minus R. A1 and R are the same on this one, so 2/5 over 1 minus 2/5, which is 2/5 over 3/5. Do your keep change flip, and you're going to get 2/3. All right, so it's pretty basic. I think it's actually easier than a lot of the other things that we did in the sections before this. Okay, last thing we want to look at is the converting repeating decimals to fractions. So it turns out that a repeating decimal, like 0.2 repeating, is actually a geometric series. And in fact, it's an infinite geometric series. So we know 0.2 repeating, what it really means, obviously it means, 0.22222 forever. But you could break that up as a sum of separate decimals. It's 0.2 plus 0.02 plus 0.002, etc. Well, each of these are fractions. This is 2/10, 2/100, 2/1000, and so on. And it just keeps going. But this is exactly a geometric series. We know the first term is 2/10. To get the next term, we multiply this by 1/10. So the R value is 1/10. So this entire infinite sum, the infinite sum represents what that decimal is. Every non-terminating decimal is an infinite sum, and it's an infinite geometric series, in fact. So that means we should be able to apply our formula. Notice that, as I said, let's write it out. A1 is 2/10, and the R, what we're multiplying each time, is 1/10 on this particular one. And 1/10 is less than 1, so we know this converges. This whole thing should converge to A1 over 1 minus R. So if we put all of that in there, that is 2/10 over 1 minus 1/10. Okay, so let's clean this up. Denominator will be 9/10. Do keep change flip, and the 10s cancel, and you end up with 2/9. And so you can test this. Take your calculator and try 2 divided by 9, and you get 0.2 repeating. Okay, so that was pretty basic, and you may have already known that. You may have already known that trick of 0.2 repeating being 2 over 9. So let's try one that has 2 digits repeating. See if we can find something similar between them. So again, you can break this up as an infinite sum. The chunks just get bigger. So you break it up by the repeating part, so 0.47 plus 0.0047 plus you're putting 2 new zeros each time. And so what that ends up happening then is you put 2 new zeros on the denominator each time down here. So we have 47 hundredths for the first one, then 47 ten-thousandths, 47 millionths, etc. So the first term is 47 hundredths, but this time the R value is 1 over 100. The 100 is coming from the fact that you have 2 decimal places. Right? The number of zeros is, think of it as the number of decimal places there. We're multiplying, since we're adding on 2 zeros each time, we're getting that by multiplying by 1 over 100 on that. Okay, so again, we know A1 is equal to 47 over 100. We know R on this one is 1 over 100, which is definitely less than 1, so it's going to work again. So this whole thing will add up to A1 over 1 minus R, which is 47 over 100 divided by 1 minus 1 over 100. Okay, so that gives you 47 over 100 over, this would be 100 over 100 minus 1 over 100, which will be 99 over 100. Right, you're taking, since you had 100 over 100, you're just removing 1. That's 99 over 100. Do keep, change, flip, and you end up, the 100s cancel. You get 47 over 99. We had 2 over 9 here, and 47 over 99 here. Again, if you don't believe you did it right, check it. 47 divided by 99, we should see these repeating. 47, 47, 47, and you do. So notice there is definitely a pattern here, and that pattern has to do with those 9s. To get repeating decimals, you need to have 9s in the denominator. And the number of 9s you have should be equal to the number of repeating digits. So this is going to be our shortcut. I'm not going to make you go through this whole process. I wanted you to see how it does tie into, like what you're really doing is you're doing an infinite geometric series and adding that together. That's how we're actually getting these to converge to these fractions. But on the exercises, let's try using the shortcut because the process is literally the same for each one. So we can see with this one, we have 2 repeating digits. So we know it's going to be the part that repeats divided by the number of digits that are here. So that would just be 39 over 99 and 99. And we can actually test to see if this works. 39 divided by 99, and you can see indeed it does work. It's that repeating decimal. Now obviously that one reduces, so you probably should fully reduce it. Sometimes they're reduced, sometimes they don't, but this is really 13 over 33. The only problem with reducing it is now you lose that nice pattern with the 9s, but these are equivalent fractions. Okay, now, so what happens if we have more repeating digits? Well, it works the same way. 117 is what repeats, but we have 3 digits repeating, so put 3 9s under it. So let's test that one. 117 divided by 999, and you get that exact thing repeating. So real easy, nice trick. Okay, let's try, I think we have maybe 3 more. Okay, the next one has a 0 in it. So, you could think of it as write the repeating part out because it is, 048, 048, 048. So 048 is what repeats over. We have 3 digits repeating, so it is 999 again. But we don't write numbers with the 48 in front, so don't leave that there. Just put it as 48 over 999. 48 divided by 999. And you can see that does work. This one seems like that should reduce. Yeah, so it's really 16 over 333. Okay, the last one. Well, this one's not hard, but it is kind of mind-bending. So according to what we just did, we said that you take the part that repeats and you divide it by 9. Well, wait a second. That's 1. So what this actually shows is 0.9 repeating is equal to 1. If you don't like that, if you don't agree with it, then go back through the entire argument that we had before with the other one, where you actually write the geometric series out. You can prove it has to converge to this. Right? The way that it would work is A1 would be equal to 9/10. That would be the first term in the sequence. The R value would be 1/10. And we know then this thing should converge to S infinity, which is A1 over 1 minus R. Plug all the numbers in, 9 over 10 divided by 1 minus a tenth, and simplify that, and you get 1. So 0.9 repeating is exactly equal to 1. And what this means is every number actually has two different ways of writing it. Every integer would have two different ways of writing it. You want the number 7? Well, that is exactly the same as 6.9 repeating. Kind of strange, kind of hard to wrap your head around, but it is true. Okay, one last example. It's a little bonus here. I think there are some on the homework that may show up like this. I don't remember, so it may just be a freebie, but in case this happens. So look, on this example here, we have a part of it that doesn't repeat, and then it starts to repeat after that. And this is very, very common with repeating decimals. Usually the first part won't repeat, but then it eventually starts repeating. So how are we going to handle this? Well, one way to do it is we would like the decimal place to be just where it repeats. So I'm going to write this as 25.34 repeating, because that's what I want. I want just the decimal part repeating. Well, but how can I do that? Well, the way I can do it is I divide it by 100. Right? If I divide that by 100, it moves that decimal place back, and it would be equal to this. 25.34 repeating divided by 100 has to be the same as this. Now, I'm going to write that divided by 100 out in front just because it'll be easier to keep track of things here. Okay, so then how am I going to deal with the 25? Well, this is really the sum of two numbers. This is 1 over 100 times 25 plus 0.34 repeating. Right? All of this exactly the same as that. And we know exactly how to handle this repeating decimal now. We have a trick for it. So leave all that the way it is. And we know that this should just be 34 over 99. Now you just use algebra and keep everything as a fraction. So get a common denominator, which is obviously 99. So you'll have to multiply 25 by 99, which should give you 2,475. All right, then you can add those numerators together. So that gives you 2,509 over 99. And then you can multiply the fractions, and that's nice and easy. Top stays the same. The bottom, you just add 2 zeros onto the 99, and there you go. And then you can obviously test this to see if it does actually give you that. So we've got 2509 divided by 9900. So we're looking for 25, and then it repeats 34, 34, 34, 34. So using that trick, you can then change any repeating decimal, no matter what it looks like. You can convert it into a fraction. All right, I believe that concludes this set of notes. So hopefully that helps with the homework. If you are having trouble, make sure you contact your teacher.